All right, next up we have acid-base reactions. We're going to start with neutralization reactions. We've talked about these before. A neutralization reaction is a double replacement type reaction. And so with a neutralization reaction, we're going to look at the reaction between an Arrhenius acid, a acid that has H in it, and an Arrhenius base, a substance that has OH minus in it. And so here's how it works. Neutralization. So we haven't talked about pH yet. pH 7 is neutral. So it says that an acid will neutralize the properties of a base when they react, and vice versa. Meaning if you take an acid, which has a pH of less than 7, and add a base to it, what you make has a pH closer to 7. Or if you take a base, which has a pH of greater than 7, and add an acid to it, the pH will be lowered closer to 7. So here is the general equation that we'll use. Take an acid, react it with a base, and you're going to make water. And I don't want to put salts, because if I put salts, you might be thinking of sodium chloride, and it's not always sodium chloride that's produced. So I'm going to put a salt. And by a salt, I mean some ionic compound. So how it works, actually, let's do an example and I'll show you exactly how it works. Letter A. Let's write the balance equation for each of these reactions. First one we'll do together. Write the balance equation for the reaction between nitric acid and potassium hydroxide. So I'm going to give you names to help you practice with writing formulas. So what is the chemical formula for nitric acid? So ic acids contain 8 ions, and I'm not talking about the number 8, I'm talking about ATE. So nitric acid, and these reactions occur in solution, so your acid and base will always be solutions. I shouldn't say always, but most often they are. So solution of nitric acid and potassium hydroxide. And so here's what we have. So here's what happens. The H from the acid and the OH from the base combine to make water. And then the cation of the base and the anion from the acid make our salt. In fact, the definition of a salt is a substance that contains the cation from a base and the anion from an acid. So in this case, we make potassium nitrates. Water in this reaction is a liquid. Potassium nitrate is a soluble salt, and so here is our balance equation for this reaction. All right, try some on your own. I don't think I'm going to have you write net ionics here. If I decide to do that later, we'll do that later. Letter B, write the balance equation for the reaction between solutions of hydrochloric acid and calcium hydroxide. Go ahead and pause the video and do that now. Here's our balance equation. We have a reaction between a monoprotic acid. That term monoprotic means a substance that has one hydrogen, like hydrochloric acid, nitric acid. They're both monoprotic acids. A reaction between a monoprotic acid and a group 2 hydroxide. This reaction is going to occur in a 2-to-1 ratio, as we see here in our balance equation. This will be important later on. Be mindful of the stoichiometry of your acid-base reactions. All right, letter C. Go ahead and write the balance equation for the reaction between sulfuric acid and lithium hydroxide. Go ahead and pause the video, do that now. All right, so this time we have a reaction between a diprotic acid. Notice sulfuric acid has 2 hydrogens, and a group 1 hydroxide. This reaction will occur in a 1-to-2 ratio, acid to base, and you end up with that equation. All right, let's try one more. Letter D, write the balance equation for the reaction between acetic acid. Acetic acid contains acetate. Acetic acid and sodium hydroxide. Go ahead and pause the video and do that now. Of ways of writing the formula for acetic acid. I like this one the best, better than putting the H in the beginning. Technically in acetic acid, not technically, but in reality, this hydrogen here is not bonded to carbon, so we don't want to put it at the beginning. That seems kind of weird to put it there. Instead, it is bonded to oxygen, and so that's why we put the hydrogen that is going to be donated at the end. So we make water and sodium acetate. So there are some examples of neutralization reactions. One of the most common laboratory practices in chemistry is something called a titration. So we're going to do a titration to determine one of two things. It says here a method of determining either the moles of some unknown chemical or the concentration of some unknown solution, that solution being an acid or a base. So here's how it works. I'm going to read the part that's not in parentheses first because then it can go either way. It says an acid solution whose concentration is known is added to an unknown base, which is either a solid or dissolved in solution. Or it could be the other way around. A base solution whose concentration is known is added to an unknown acid, which is either a solid or dissolved. So sometimes you're adding an acid to a base, sometimes you're adding a base to an acid. You continue the process in number 2, adding acid to base or base to acid, until you have an equal number of moles of acid or base in the solution. When you have stoichiometric amounts, so it doesn't necessarily have to be equal moles, it has to be stoichiometric amounts. By stoichiometric amounts, I'm thinking about the mole ratio for that reaction. When you have stoichiometric amounts of acid and base in your solution, this is known as the equivalence point. At the equivalence point of a titration, you have an equal amount of moles of acid as base based on the stoichiometry of the reaction. At this point, all of the acid added has neutralized all of the base. Or if you're doing it the other way around, all of the base that you've added has neutralized the acid that was present at the beginning. Some vocabulary terms. A standard solution is a solution whose concentration is known. So you have to know the concentration of one substance to find the concentration of another substance. Number 5, very important. How do you know when you've added an equal amount of acid to base? Let's say you have 25 milliliters of sodium hydroxide and you're titrating that with hydrochloric acid. How much hydrochloric acid does it take to neutralize the 25 milliliters of base? Is it 25 milliliters? Well, that would only be true if what? Answer that question for me. You have 25 milliliters of sodium hydroxide. What has to be true if it takes 25 milliliters of hydrochloric acid to completely neutralize it? Well, that would only be true if both the sodium hydroxide and hydrochloric acid had the same concentration. So you don't necessarily add an equal volume of acid to base, especially if they have a different concentration. That's not true. You're not going to have an equal number of moles. So how do you know when you have reached the equivalence point? How do you know when you've completely neutralized the base? To do so, you're going to use an indicator. So it says you can detect the equivalence point by using an indicator, such as litmus. I'm going to use phenolphthalein in our experiment. And remember that the indicator will change color at, or at least very near, the equivalence point. Now, make a note. The point at which the indicator changes color is known as the end point. So the pH where phenolphthalein turns from colorless to pink is called its endpoint. And if we pick the appropriate indicator, the endpoint for the indicator will be close to the equivalence point of the reaction. All right, so let's take a look at a couple types of calculations that we'll perform involving titrations. Again, we're going to do both of these in our experiment. First one, determining the concentration of an acid or a base. Um, this relationship here that we're writing assumes that the acid and base react in a 1-to-1 ratio. So neither this nor this are entirely true for a reaction that does not occur in a 1-to-1 ratio. So make sure you're aware of that. So we're talking about a situation where you have, say, a monoprotic acid and a group 1 hydroxide, such as our first example, nitric acid and potassium hydroxide. They're going to react in a 1-to-1 ratio. And at the equivalence point, moles of the acid equals moles of the base. Now, how do we determine the number of moles of acid or base that you have added or that you have available? We can take the concentration of the acid times the volume of the acid, and that'll give us moles of the acid. So I'm going to write this equation here a little bit different. Instead of M times L, I'm going to write it this way. MAVA, molarity of the acid times volume of the acid. First of all, this is moles of acid equals MBVB, which is moles of base. Concentration of base times volume of base. So a couple notes about this equation. Again, this is only true for reactions that occur in a 1-to-1 ratio. Secondly, this is only true for situations where both your acid and base are in solution. If one of them is a solid, then technically we can't use this form. So we'll see an example of that. Actually, we'll do that right now. So let's say that the acid that you are working with is a solid. Well, we can't say MAVA equals MBVB. Suppose you're titrating a solid acid with a solution of a base. The form that we'll use is this. Get rid of that. But this is true. Moles of acid equals MBVB. Conversely, if your base was a solid and you're titrating it with a solution of an acid, then since the base is solid, we can't use MBVB. Instead, we get MAVA equals moles of base. So 3 different equations depending on your acid and base, whether they're both in solution or if one is a solid and the other is a solution. The other calculation we can do using a titration is to determine the molar mass of an unknown solid acid or solid base. We've done this before, determining the molar mass of an unknown substance. So we're going to use that similar approach, but how we're going to get to moles here is different than what we did with gases, for example. So with gases, we use ideal gas law to find moles. Here we're going to use the equivalence point. So first step is to determine the mass of the unknown acid or base. So we need grams of that. Then we take that, we titrate it with an acid or base solution whose concentration is known. Of course, you're going to titrate to the equivalence point. And based on the concentration and volume of the acid or base that you're using, you can find moles of the acid or base. And then once we know the mass of the unknown acid or base and moles, take those and divide them. Remember, molar mass is mass of the substance divided by moles. So mass, we get to there, we measure that. Moles, we get here, we calculate using the concentration and volume of our titrant. Titrant is the chemical that we use or that we're dispensing through the burette, which is the piece of glassware that we use for a titration. So I'll show you that, the glassware that we use in a titration when we are doing our experiment. All right, so let's do some examples. Letter A. What is the concentration of an HCl solution? So that is your acid. We're trying to find that. If 25.0 milliliters of it are titrated to the equivalence point by 45.0 milliliters, 0.200 molar sodium hydroxide, which is our base. So I suppose what we want to do first is determine the stoichiometry of this reaction. More often than not, the reaction will occur in a 1-to-1 ratio. We don't have to write the balance equation unless it asks for it. So what we see here is we have a monoprotic acid, 1 hydrogen, a group 1 hydroxide, and so this reaction will occur in a 1-to-1 ratio. So that means that moles of acid equals moles of base at the equivalence point. So both acid and base are in solution, so we're going to use, I think I used lowercase a's last time, but that's fine. We'll use capital A's and capital B's. So we're going to use this form. Molarity of acid times volume of acid equals molarity of base times volume of base. Now some of you might be thinking, oh, I'm familiar with this equation. That's the equation we use for dilution. Well, not exactly. So for dilution, the chemical composition of the solution doesn't change. Just the concentration and volume does. Here we're comparing different substances, acid and base. So please do not label this M1V1 equals M2V2. It's MAVA, moles of acid, equals MBVB, moles of base. All right, think about what we're solving for, rearrange the equation, and do this calculation. Please pause the video now. All right, so here's our setup. We're trying to find the concentration of the acid, so we're solving for MA, so I've taken that equation and rearranged it. Plug in my values. Notice that I left the volumes in milliliters. Since those units are going to cancel, we don't have to convert to liters here. So go ahead and leave it in milliliters, and we get 0.360 molar is the concentration of the HCl. All right, now we're going to use that for our next problem. Suppose 20.0 milliliters of the previous acid, so we're talking about the 0.36 molar HCl, is used to titrate 1.00 grams of an unknown base to its equivalence point. Now it's not written here, but we'll assume that this reaction occurs in a 1-to-1 ratio. Calculates the molecular weight / molar mass of the base. Now, which form of the equation are we going to use? MAVA equals MBVB, or moles of acid equals MBVB, or MAVA equals moles of base? Figure that out, set it up, see what you get. Go ahead and pause and do that now. All right, here's our setup. So we have an acid who is in solution, so we can use MAVA, but our base is a solid, so we can't use MBVB. So we're going to use MAVA equals moles of base. So we're going to multiply the concentration of the acid times the volume of the acid. Notice what I did here. Though it worked in the last problem, because the units of volume canceled, we cannot use milliliters here. If you do, you're going to get a weird answer. So make sure when using this form that you put the volume in liters. So we get 0.00720 moles of acid technically, but because this is at the equivalence point, this is also moles of the unknown base. Take grams of the unknown base, divided by moles of the unknown base, and we get the molar mass, 139 grams per mole, which is numerically equivalent to the molecular mass, which would have units of AMU, so 139 AMU for the molecular mass. All right, that concludes this lesson. Thanks for watching.